Logistic growth. So what about logistic growth? So population growth, it's usually modeled with y equals some a e to the kt, where k being a positive number implies population growth. If it's negative, it's population decrease, or it's usually related to radioactive decay, or for a chemical reaction, you can relate this to the loss of a reactant and then the production of a product, in your in your flask. All right. Well, but the thing here, what happens in the long run? I mean, ideally, this is not the best model to describe a population growth. I mean, it's a good example to get used to exponential functions, exponential equations. But if we put the realism, this function right here does not take into account limited supplies. You cannot go to a community and live forever, right? People is gonna die at one point, or the carrying and takes into account the carrying capacity of a place like here, the classroom. How many people can I get? 40. There's 48 seats. I mean, I could have more students sitting on the floor to take the class, but there's not going to be a space for infinitely many students taking my class, right? So there's a carrying capacity for the classroom. Well, so what about this? Well, so this curve, it's modeling a different way, and arises when the rate of change at which population is growing directly proportional to a product between two quantities. That is, the product between the population size and the difference between the population and its carrying capacity, giving us this differential equation. Actually, I'm giving you both versions because you may see different versions together. Number one, notice K and R, because L, which is the carrying capacity of the community or the space, it's a constant. There's a maximum number and it's a constant. So I'm factoring a constant, multiplying it with K, which by absorption gives rise to just another constant right here, right? Okay, so solving this differential equation, which by the way, it's quite of a big process. It involves partial fraction decomposition, gives this equation, this function. That's the solution. And as you can see, unlike the baby exponential function, the baby growth, which actually diverges to infinity, well, here, look at what happens here. We have the exponential term in the denominator. What happens? The denominator gets larger, larger, larger. Okay? So we divide by a larger number, we get a smaller number. So in that sense, we are converging to some value, not diverging to infinity like the other exponential model. All right? So let's have a look at one example that deals with the logistic growth. Okay, so the rate at which a population P of fish in a lake is growing is directly proportional to the product of the population and the difference between the population and its carrying capacity. All right, a lake is initially stocked with 100 fish. After 2 years, there are 250 fish. And the carrying capacity of the lake is known to be 500 fish. So think about a lake. It's bounded. It's not an infinite lake. All right. So we can have infinitely many fish in there. All right. So that exponential model from before, it's not the correct one. Okay, number one, write a differential equation to represent this situation. And we're going to talk about the stability of the solution. So number one, so they're telling us that P of 0, that is the initial population. How many fish initially? 100, all right? Okay, P of 2, that is after 2 years, we have 250 fish. And well, the carrying capacity, that is L, which is kind of a letter to denote some limit, some maximum value, okay? So it can only hold up to 500 fish, all right? So the differential equation in question, it's dP over dt equals Kp times L minus P, all right? So, well, putting numbers, dp dt equals to kp. In this case, p is variable. The p is a variable. That's the population size of the fish. But L, that's 500 minus on p. All right. So that's the differential equation that for the situation. So for part B of the problem, they're asking us to examine this differential equation and identify any equilibrium solutions and draw a phase diagram. The phase diagram to determine the stability of the solution. So, all right. So what do? Set this guy equal to 0. So Kp times 500 minus P equals to 0. All right. So, so Kp equals to 0, or 500 minus P equals to 0. So P equals to 0 and P equals to 500. So these are the equilibrium solutions. We're going to have an asymptotic at y equals to 0 and another asymptotic at y equals to 500. All right. Okay, so let's see. So phase diagram. Okay. So let's plot the critical values. Those are 0 and 500. Okay. And well, let's test some values. Okay. So say -1. Okay. So at -1, at +1, and at 501. Okay. So for P equals negative, I don't think there's a way. It wouldn't make sense to test negative fish, but I want to see the stability anyway. So, -1. Okay, so negative, this is going to be a negative here. 500 minus -1, that'll be +1. That's positive, so it's going to go in this direction, right? What about at 1? So 1 times, which is positive, 500 minus 1, that's positive, all right? So unstable at 0. And what about at 500, okay? So at 500, after 500, for 501, that's positive 501. However, 500 minus 501, is that negative? So, stability. So when we reach the maximum capacity, in this case, that's where we're going to have a stability. Think that now that we have this in a real life situations, this concept of stability, instability makes more sense. All right. So, okay, what's the next part? All right, so the next part is solving the differential equation. However, I'm not going to solve the differential equation because it's going to take forever. So instead, okay, so I'm just going to use the solution to it, which is at the bottom of the definition. P equals to, okay, P of t equals to, what was that? L over 1 plus A e to the negative kt. Okay. And well, we know the value for L, right? That is 500 over 1 plus A e to the negative kt. And just like, the rest of the problem is going to be very similar to what we have done with the fictional model, the baby exponential model. So that's because we're going to use the initial conditions to find A and negative k. All right, and the value of k. All right, so with, what's it called, with P of 0 equals to, what is that? Is that equal to 100? That means P of 0 equals to L, which is 500, over 1 plus A, we don't know what A is, e to the negative k times 0. And that equals to, what is that, 100? Equals to 500 over 1 plus, e to the 0, which is 1, times A, that equals to A. So we can solve for a, the coefficient of the exponential, which, by the way, this a right here is not the initial population, unlike the other exponential model. The number that multiplies the exponential with a positive exponent, that's the initial population, not here. So what do? Okay, divide by 1, or rather, divide by 1 and cross multiply. All right, so 100 times 1 plus a equals 500, which means 100 plus 100a equals 500, 100a equals 400, and a equals to 4, isn't it? So far we have P of t equals to 500 over 1 plus 4 e to the negative kt. So there's one more piece of information, that is what's the rate, what's the rate of increase, right? So that is the value of k. And I know you're looking at a negative k, well, that means decrease. No, but look at where the k is. It's in the denominator. If we think of moving into the numerator somehow, well, we end up with a positive k. There's some increase, but limited to a maximum of 500. And for this, we're going to use the second condition, that is with, what was that? P of 2 equals to 250. That is, P substitute 2 equals to 500 divided by 1 plus 4 e to the negative k times 2. Okay, so what's P of 2? Let me continue here. So that's 250 equals to 500 over, what is that? 1 plus 4 e to the negative 2k. Well, so we have another exponential equation to solve for the variable k. Yes, I'm going to do the whole work for this. Okay, so that is 250 times 1 plus 4 e to the negative 2k equals 500, and 1 plus 4 e to the negative 2k equals, dividing both sides by 250, is that 250? Okay, and cancelled from the right side. The rest of the problem, it's a bit of arithmetic. Subtract 1, that is, let's see, what should I do here? Oh, it's actually 2. You're right. I don't know why I was subtracting. Yeah. It's Monday, right? 4 e to the negative 2k equals to 1, and then e to the negative 2k equals 1/4, and negative 2k equals ln of 1/4. I'm going to add one more page on my notes. You guys might want to continue on the back side of the page. Okay, so k equals to negative 1/2 ln of 1/4. So that's the value of k. All right. And if we use a graphing calculator for this should be approximately 0.693. I'm going to leave it like this in 3 decimal places. Okay, 0.693. All right. What's next? We can finally call it P of t equals to 500 over 1 plus 4 e to the negative 0.693 t. And this is the function we're going to use to estimate the population size of fish given this carrying capacity of 500, etc. Which in this case, look at the model. It's not like the model you learn in intermediate algebra or in pre-calculus. Actually, depending on the situation, some pre-calculus programs include this logistic growth, this other model. But in general, we only cover the the baby exponential. Usually, this is covered in a differential equations class. All right. Looks like this is the end of the